Hey friends, welcome to the YouTube channel all about electronics. So in this video, we will learn about the Cascode current mirror. Now in the earlier video of the current mirror, we have seen that there are a couple of issues with the simple current mirror. The first is the output impedance. If we see the output impedance from this end, then it is the output impedance of this MOSFET M2. Now many times, this current mirror circuit is used as an active load to drive the other circuits. For example, this PMOS current mirror can be used as an active load to drive the common source amplifier. And if this current source is ideal, in that case, the output impedance of this current source will be infinite. And in that case, the gain of the amplifier circuit is the intrinsic gain. But when this current mirror circuit is used as an active load, then due to its finite output impedance, the overall gain of the circuit will reduce. So in this case, this R02 is the output impedance of this current mirror, while the R03 is the output impedance of this M3, which is seen from this side. So somehow, if the output impedance of this current mirror circuit can be increased, or in this case, if R02 is much greater than R03, in that case, this amplifier gain is close to intrinsic gain. The second issue is, due to the channel length modulation effect, this copied current ID2 is not the exact replica of this reference current. So if there is no channel length modulation effect, then as far as this MOSFET M2 remains in the saturation, then this copied current follows the reference current. And even if there is a change in the drain to source voltage, then also this drain current ID2 should remain constant. But due to the channel length modulation effect, as the drain to source voltage increases, then the drain current also slightly increases. So through a simulation, let me show you the effect of this channel length modulation on the current mirror circuit. So here I have set the same W/L ratio and the other device parameters for these two MOSFETs. That means here the threshold voltage is equal to 0.5 volt, while the W/L ratio for these two MOSFET is equal to 1. Moreover, here the process transconductance is equal to 200 microampere per volt square, while the channel length modulation parameter is equal to 0.02. So in this case, let me just run the simulation and let me show you the effect of this drain to source voltage on the drain current. So here, currently, the drain current ID is equal to 52 microampere. Now let me just change this drain voltage and let us see the effect on this drain current. So here, as I am changing this drain to source voltage, then as you can see, the drain current ID is increasing. So earlier, when the VDS was 3.3 volt, at that time, this drain current was 52 microampere. And as soon as this drain to source voltage becomes 5.1 volt, then this drain current is approximately equal to 54 microampere. So as you can see, as the drain to source voltage increases, then due to the channel length modulation effect, this drain current also increases. So this is the expression of the drain current including the channel length modulation effect. Now typically, the current mirror circuit is used in the integrated circuits. So in the IC, we can fairly assume that the threshold voltage Vt as well as the channel length modulation coefficient lambda is same for all MOSFETs. Moreover, here this gate to source voltage is also same for both MOSFETs. So considering the different W/L ratio for these two MOSFETs, the relationship between the drain current ID2 and this ID1 can be given by this expression, where here this ID1 is same as the I reference. Now in this expression, if this W/L ratio of these two MOSFET is same, in that case this ID2 is equal to ID1 whenever this VDS2 is equal to VDS1. That means if this VDS2 is equal to VDS1, in that case only this copied current is the exact replica of this reference current. Now here this M1 is the diode connected transistor, and since the gate and the drain terminals are connected together, so here this VDS1 is equal to VGS. Now actually the voltage at the drain terminal of this M2 depends on the external circuit, and therefore it is difficult to control or predict the voltage at this drain terminal. So basically there are two issues with the simple current mirror. One is the moderate output impedance, and second is this copied current is not the exact replica of this reference current, or in other words, it does not exactly follow this reference current. And these two issues can be resolved using the cascode current mirror. So step by step, we will understand this cascode current mirror. Now first, let us add one more MOSFET in series with this simple current mirror. And let's say some biasing voltage VB is applied to it. Now we will shortly see that what should be the value of this VB. But this circuit will serve two purposes. First is, it increases the output impedance of this current mirror circuit. And the second is, for this copied current, it reduces the voltage dependency on this voltage VDS2. Now if you closely observe this M3, then it is the common gate stage, because here this voltage VB is the DC biasing voltage. So for the AC analysis, it will act as a ground terminal. And if we see the series connection of this M2 and M3, then it is actually a cascode connection. That means if we see the output impedance from this end, then it is approximately equal to GM3 times R0 3 times R0 2. And in fact, we have already covered this cascode amplifier in the earlier video. So for more information, you can check this video on the cascode amplifier. So with this cascode connection, the output impedance is much greater than R0 2. That means there is a significant improvement in the output impedance. Second is, if the biasing voltage VB is selected properly, then it is possible to keep this voltage VDS2 very close to VGS. And hence, it is possible to make this copied current the exact replica of this reference current. So now, let us understand what should be the value of this biasing voltage. So here, if we apply the KVL around this loop, then we can say that this voltage VB is equal to this voltage VGS3 plus VDS2, that is this voltage. So for simplicity, let's say the voltage at this end is equal to Vx and the voltage at this end is equal to Vy. So clearly this Vx is equal to VGS and this Vy is equal to VDS2. So here, if we want this ID2 same as the I reference, then in that case, this Vy should be equal to Vx. Or in other words, this VDS2 should be equal to VGS. So here, if we select the value of VB is equal to 2 VGS, then in that case, this Vx and the Vy will be very close to VGS. So let us understand how. So if we see over here, then this drain current ID can be given by this expression. So clearly, because of this square term, this drain current is a strong function of this VGS. So if we apply the voltage VGS to this M2, then the drain current ID2 will start flowing through this M2. So of course, the VDS will also play a role in deciding the exact value of this ID2, but its role will not be as much as the VGS. So the exact value of the ID2 will depend on the value of this VDS2, but approximately we can say that this ID2 is very close to I reference. Now this M3 is also connected in series with this M2. That means the same current ID2 will also flow through this M2. Now here, for a time being, we are assuming that the drain terminal of this M3 is connected to some fixed voltage such that the M3 is already in the saturation region. So since the same current is flowing through the M3, so intuitively we can say that this voltage VGS3 should also be very close to VGS, right? Now moreover, here this VB is equal to 2 VGS. That means 2 VGS is equal to this VGS3 plus VDS2, or we can say that it is equal to VGS3 plus Vy. Now if the voltage at this end is slightly greater than VGS, in that case this drain current ID2 will be more than I reference, right? That means whenever this Vy is greater than VGS, then this drain current ID2 will increase. And since this VGS3 is equal to VB minus Vy, so as the voltage at this end or the Vy will increase, then the VGS3 will reduce. and since there is a reduction in this voltage VGS3, so it will try to keep the ID2 same as around I reference. So in this way there is a negative feedback, and in a way it will try to keep the ID2 same as the I reference. That means in a way, when we set the value of VB is equal to 2 VGS, then it ensures that these VGS3 and VY are very close to VGS. And due to that, this ID2 is following this I reference. So I will also show you the same thing using the simulation. But first, let us talk about the drain voltage VD3. Now so far we have assumed that the voltage VD3 is fixed and it is selected such that the M3 remains in the saturation. So to keep the MOSFET M3 in the saturation, this voltage VD3 should be greater than or equal to this VB minus VT, and this VB is equal to 2 VGS. That means this voltage VD3 should be greater than or equal to 2 VGS minus VT. Now if you are aware, then this VGS minus VT is equal to overdrive voltage. So in terms of the overdrive voltage, this voltage VD3 should be greater than or equal to 2 times this overdrive voltage plus VT. That means to keep the MOSFET M3 in the saturation, the drain voltage VD3 should be greater than or equal to 2 VGS minus VT. Now if the voltage at the drain terminal of this M3 is less than this 2 VGS minus VT, then the M3 will operate in the triode region. But still, this current ID2 will be very close to I reference, because still this M2 is operating in the saturation region. So unless this VD3 drops substantially, this circuit tries to maintain the ID2 very close to I reference. But the downside is that if this M3 operates in the triode region, then the output impedance, which is seen from this side, will also reduce. That means to get the high output impedance, this M3 should also operate in the saturation region. Now in the saturation, if this VD3 is increased further, then of course this ID2 will also increase, but it is not as much as it was the case in the simple current mirror. That means with the increase in this voltage VD3, there is a very small change in this ID2. So let us understand the same thing using the simulation. So first of all, to set up the value of VB is equal to 2 VGS, we should know that what is the value of the VGS. So if we measure the voltage at this end of this diode connected transistor, then we can find the value of the VGS. So if I just run this simulation, then for a 50 microampere current, the voltage which we are getting is equal to 1.19 volt. And here the MOSFET parameters are same as the previous case. So now let us set the value of VB, which is 2 times this value. So here the value of the VB is selected to 2.4 volt, which is very close to 2 VGS. And here this voltage VD3 is selected such that this M3 remains in the saturation. So with these values, if I run the simulation, then this drain current ID2 is very close to 50 microampere. And if you see over here, then the voltage Vx and Vy are also very close. So now let me just change the value of this VD3 and let me show you the impact on this drain current. And first of all, let us reduce the value of the VD3 and let us bring this M3 very close to triode region. So as you can see, even if I am reducing the value of the VD3, then also the drain current ID almost remains same. On the other hand, if I increase the value of the VD3, then there is a very small change in this ID2. That means there is a very small change in this voltage VD3 on this ID2. The reason is that as we increase the value of the VD3, then of course the drain current ID should increase. And due to the increase in the VD3, the voltage at this end or the Vy should also increase. But as the voltage Vy increases, then the voltage VGS3 will reduce. And due to that, it will try to maintain the drain current ID2 very close to I reference. That means with the change in the voltage VD3, there is a very small change in the drain current. And in a way, this circuit tries to maintain the copied current very close to the reference current. So now the question is how to generate a precise value of this voltage VB. Well, it can be generated using this circuit. So here one more diode connected transistor is connected in series with this M1 and the gate of this M4 is connected to the M3. Now since the current which is flowing through the M4 is same as the I reference, so this voltage VGS4 should also be equal to VGS. That means if we see the voltage at this end, then it is equal to VGS plus VGS, that is equal to 2 VGS. And exactly the same voltage is required to bias this M3. So this circuit is known as the cascode current mirror. And using this circuit, it is possible to get the value of the ID2, which is exact replica of the I reference. Moreover, this circuit also improves the output impedance. So now let me just show you the simulation for the same circuit. So here the device parameters of all the 4 MOSFETs are kept same, and these parameters are same as the previous case. So if I run this simulation, then you can see this current ID2 is very close to I reference, and if you observe the voltage at this end, then it is very close to 2.4 volt. And here if I change this voltage VD3, then also there is a very small amount of change in the ID2. The only downside of this circuit is that to keep the MOSFET M3 in the saturation, the voltage at this end or the VD3 should be greater than or equal to 2 VGS minus VT. So when such circuit is used for driving the amplifiers in the IC, then the available voltage swing for the AC signal will reduce. And it is particularly important in the ICs where the operating voltages are very low. So that is the only downside of this cascode current mirror. But I hope in this video you understood the working as well as the advantages of this cascode current mirror. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.